quickly going to recap. Right, we said that the distribution of electrons are not even. Thus, we have positive and negative side. We call them polar or a dipole. Right. Then we said adjacent molecules, so molecules next to each other, will attract each other electrostatically. And here, I don't know if I did a drawing in the video. I think I did, where I drew the molecule like this. Yes? More or less. We said that is negative, that is positive, and then there's an attraction force between them. That is an intermolecular force. Okay, so inter means between, molecule, force. So between molecules we have a force. All right, did you enjoy the video more than actual class?
Yes.
So, I'm just glad I had a video to play, but I laughed because I listened to the video before I sent it to you, and you hear me speaking to the other learners. Yes. And did I make any inappropriate comments? Because that does happen. Nothing. Okay. Yes, Bukubuso. Yeah, Bukubuso. Your hand was up.
I'm sorry that I'm late for my meeting. To get my back. It was in class.
2.
Did Boki take physics last year?
Who? Boki. He's. Ria Boka did, but he took in. There's a Boki as well. Bokang. He takes science. Bongani took science. Ria Boka did take science, but he left in grade 10. There was a big class. Anyway, all right. These forces are called intermolecular forces or van der Waals forces. They influence the melting and boiling points. And the stronger the intermolecular forces, the higher the melting and the boiling points. Okay, right. Then we're going to look at 4 different types of intermolecular forces. London dipole hydrogen bonding. They are all intermolecular forces and van der Waals forces. And iron dipole forces are intermolecular forces, but they are not van der Waals forces. Okay, so they just have a different subheading. Then we spoke about intermolecular forces and intramolecular forces or bonds. So this is bonds. Yeah.
Isn't van der Waals forces and IMF the same thing?
No. So you have intermolecular forces, and then under them you have van der Waals forces, and then you have ion dipole forces. So van der Waals forces is part of intermolecular forces, okay, but ion dipole forces are not part of van der Waals forces, but it's part of intermolecular forces. You get the idea. All right. Then I just want to check on the next page. Did I go through all of the tendencies? Yes. Okay. All right. I just want to quickly recap again that you saw that with the noble gases, all of them, they are symmetrical, the molecules. Thus, they are non-polar. Okay. So, say again. And thus, they have London forces. Oh, my word. We did so much. Okay. But I feel like I missed out, like I have FOMO of the lesson. All right, and you saw that as the molecule gets bigger, the melting and the boiling points increase as well. Okay, then the halogens, if we look at them, they are linear, their structure, thus they are symmetrical, and thus they are non-polar, and they have London intermolecular forces. London forces weak or strong? Weak. Okay. Again, as it gets bigger, the melting and boiling points increases. Then carbon halides, they have, what's their shape? Tetrahedral. And thus they are symmetrical, non-polar London forces. Okay, same thing with hydrocarbons, tetrahedral, symmetrical, non-polar. Linear. Sorry. I just looked at the first one. Linear and symmetrical non-polar London forces. Okay. Yes. Because the first one, that one looks like this, tetrahedral. But if you look at the next one, it looks like this. Now it becomes a bit more linear. Okay. Right, then group 4. So group 4 halides. Tetrahedral, symmetrical, London forces, boring. Okay. Then here we get to the interesting parts. Okay. So you saw that these ones are typed in cursive. Italics, thank you. Okay, and there's something fishy going on there. I'm so proud of you guys. Okay, the shape there we saw is what? Pyramidal. Okay, because of the what? Because of the lone pairs. Okay, so because of the lone pairs, it's pyramidal, and that is why it is asymmetrical and thus very much polar. Okay. Did we go into why this was special? Hydrogen bonding. Sort of? Okay, I will stop there again. Okay, so why is it a bit fishy? Because as you see, it goes bigger. This part makes sense. It increases. But this one here is an exception. That should actually fit in there. And that should fit in there. So it's not following the trend as it should. So this one is an exception. Okay. Right? And same with water. If we look there, water is what shape? Angular. So it's asymmetrical. So it's very much polar. Okay. Again, if you look at these three, then as it becomes bigger, it increases. But not water. That should actually be all the way here and all the way there. So it's not following the trend as it should. And then the last one, group 7 halides, we have linear, but because it's two different molecules, it is asymmetrical, so it's very much polar. Okay, and again, if you look at these three, then as it becomes bigger, it increases, but this one doesn't follow the trend. That should be there, and that should be there. Okay, so this one again is fishy. Now, if we look at it on the product table, you can see all of them have hydrogen bonded to what? They're bonded to nitrogen, oxygen, fluorine, NOF, NOF. Okay, so those three things there is the red lights going off. So, okay, what's happening with them? Why are they special when they bond with hydrogen, but not all of them below them? All of it below them. Okay, we looked at London forces, and we said with London forces, they also call it, I said it's called temporary dipoles or induced dipoles. They also call it dispersion forces. I don't know, I saw that they like to use dispersion nowadays, but London is still the main one that they use, but I see they use dispersion forces. Okay, so that is temporary, so it's not permanent, it's not always there, it's there for a few seconds, then it goes away. Temporary dipoles formed as a result of uneven distribution in electrons and atoms. Yes, Abugamuso. Previous page.
What is the MR stands
MR,
for?
molecular mass, or the molar mass, doesn't matter. Or formula mass. It also has 3 names. Okay. Right, so London forces, we saw that because they are not permanent, because they can, all the electrons that are pushed to the side can then just go back to where they were. That is a very weak electrostatic force. But then the higher the atomic number, the bigger the molecule, the stronger the dipole formed. And I see you all drew the picture there at the bottom. The bigger it becomes, the bigger magnet it forms. All right. And then this type of van der Waals force exists between symmetrical or polar molecules as noble gases, diatomic, non-polar particle. And I think here we went to the previous page and then we wrote it down where they all are. No. All right. So this here is just drawings for you to show that, okay, here we have helium and then the electrons are just pulled to the side. And the same thing here, you can see there's the electrons being pulled to the side. This is the protons and the electrons are pulled to the side. Okay, then we did dipole forces. Okay, so dipole is between two poles. So a molecule like hydrochloric acid that has two poles and another hydrochloric acid that has two poles. So it's between a dipole and a dipole. There you have that intermolecular force. Okay. It's also relatively weak. It's not as weak as London forces because it is a permanent dipole, but it's not that strong. And it is formed between polar covalent molecules where the difference in electronegativity is greater than 0 or smaller than 1.7, and the molecule is not symmetrical. Okay, so you can see there we have the slightly positive side here, slightly negative, slightly positive, slightly negative. And then in between there we have that intermolecular force. That intermolecular force, dipole force, because it's between a dipole and a dipole. We call it a dipole force. Okay, but that thing there in the middle there is a covalent bond, and that is very strong. That is difficult to break. Okay, and then we are at hydrogen bonding. Is that where we stopped? Yes. Okay, right. Now, hydrogen bonding is quite controversial, the name and where it fits in. If you go to old textbooks or if you have extra classes or extra question papers, they might say that hydrogen bonding is a type of dipole. Okay, but recently they put hydrogen bonding on its own. Okay, so previously they said that you have intermolecular forces, van der Waals forces, dipole forces, and then hydrogen bonding is one of the dipole forces. But now they've scratched that. They said no, hydrogen bonding is something on its own. Okay, it is a special type of dipole, so it's also dipole, but it's like in its own level, category, whatever. Okay, right. Now, if we consider the melting and the boiling points of these three, so if we look back to that second page, and you don't have to do that now, okay, but when we look back at them, we saw that their melting and boiling points does not follow the trend. It's like it's out of place. Okay, but their masses are where it should be, but their melting and the boiling points is not where it should be. Okay, and the question is why? Why does that happen? Okay, they are much higher than the trend in each group would indicate. If it's higher, it means it must have a stronger force. Okay, and why does it have a stronger force? This is caused by hydrogen bonding. Okay, now, just a quick pause there. We're speaking about intermolecular forces. So I started with this somewhere this week. I said a force is something that you don't see. There's not a line here and then we say there's a force. It's just an attraction that the two people can feel or the two atoms can feel, but you can't see it. Okay, so you can't break it. Okay, but a hydrogen bond has then the word bonding in it. So is it a bond that formed or is it still a force? It's a force. But why does it have the name bonding? Okay, so hold that in your head. I'm going to read and then I'm going to explain that word bond. So it is very strong force between permanent dipoles of ammonia, water and fluorine. Now you only do those three molecules in grade 11. In grade 12 we add another one, but in grade 11 it's only those three. So if you see those three, hydrogen bonding. Okay? Why is it so strong? Because the hydrogen is bonded to a very small, very strongly electronegative atom. Okay, so if we look, do you have your periodic tables with you? Like a small one. If you look on the periodic table, and you look fluorine is 4. Oxygen 3.5. Nitrogen 3. So they are all quite strong. But then also look at chlorine. What is chlorine? It's 3. So why is it not part of this packet? Okay. If you look at the 3 of them, nitrogen, oxygen, fluorine, they are all in period 2. They only have 2 energy levels, so the molecule is very small. So the valence electrons are close to the protons. Whereas chlorine in period 3 is a lot bigger. So the valence electrons are far from the protons, so that attraction is not that big. Okay, so it must be small and it must be a strong electronegative atom. So if that is bonded to hydrogen, then you have a very polar molecule. Okay, so I'm going to read further. It says, since there are few other electrons present to act as a screen to block off that attraction force, the nuclei attract the covalent bonding electron pair so strongly that the hydrogen atom is left as a bare proton, or we can say as a naked proton, creating a very strong dipole. Okay, so I'm going to draw a drawing. So if you look, I'm going to look at hydrogen fluoride. We have hydrogen and we have fluorine. Okay, zoom in there. Now they share that electron pair, but that shared pair is not very equal, because fluorine is so strong and it's so small that it pulls that electron pair so close to fluorine that hydrogen is left on its own. It's just there. It's just a small proton, and then fluorine sits with all of the electrons. So your molecule that you have there is very positive on this side and very negative on that side. Okay, so because fluorine is so strong, it pulls all those electrons to itself, and hydrogen becomes very positive and fluorine becomes very negative. Okay, so we have a very strong dipole. Okay, now we have, okay, and I'm going to zoom into this one. Now we have this extremely strong dipole, and when it comes close to this extremely strong dipole, this attraction force is like having 2 very strong magnets. This attraction force is very big. Okay, so when they come together, the attraction force is so big between them, you wonder if it's not a bond that formed, because they're so close. It's just a force. So if you zoom in, you'll see there's nothing between them, but it looks like a bond because they're so close together. You get those learners in school that you wonder, are they like stuck together like this? Big space. It is like that. Okay, I want to show something else. Okay, so it's like these 2 magnets here. Are they pasted together? No, it's just the attraction force between them is so strong that you think it is a bond. You think they're pasted together, but it's not. So that is why it's called a hydrogen bond, because it looks like a bond because they're so close, but it's actually not. Okay, so hydrogen bond is not a bond, it's a force. Okay, so I'm going to read this again. We see that these 3 have a very high boiling point. Why is that? Because of hydrogen bonding. How do you get hydrogen bonding? What is it? It is a strong force between permanent dipoles in those 3. When a hydrogen is bonded to a small, strongly electronegative atom like these 3, because that bond there between them is so uneven, because these 3 are so strongly electronegative, they steal hydrogen's electron. And hydrogen is left as a naked bare proton. It's just a positive thing, and that thing becomes negative. So you have a very strong dipole, and then the force between 2 such molecules is called a hydrogen bond. So there you can see again, very positive, very negative, negative, positive, hydrogen bond. Same. Okay. Sharp? Right, and then then specifically at hydrogen bonding and specifically at the water molecule. we have very interesting characteristics that form due to this hydrogen bond. Okay. I'm going to read, I'm not going to highlight a lot. It says that at high temperatures, the molecules move too quickly for hydrogen bonds to form. Thus, water is in a vapor phase. So, at high temperatures, they move quickly. And then we have a vapor phase. Okay, so you have gas molecules floating around, steam. Okay, but as the temperature decreases, as you make steam colder, the molecules move slower. The movement also decreases. And then they come together and they form a hydrogen bond for a split second and then they go away. And then they form a hydrogen bond and they go away. So hydrogen bonds are formed and broken continually the whole time, resulting in chain molecules. This is the liquid phase. Okay. Then as you make this water colder, so the temperature goes down even more. Then the molecules cannot prevent hydrogen bonds from not forming, and then it links the molecules into 6-sided rings. And this is the solid phase. Okay. Now before I go to the next page, I want to show you here at the bottom. So there you can see the water molecules. They move a lot of space between them, no chance for a hydrogen bond gas phase. Then as soon as they move slower, they can link up to form the hydrogen bonds, or they can form hydrogen bonds, but then they break away again. So this is the liquid phase. But when it cools down even more, then it makes these 6-sided rings like that, water crystals. Okay, so this is what ice, if you zoom in, this is what ice actually will look like. Okay, and the reason why it makes these 6-sided rings is because the water molecule is bent or angular. Then it forms these 6-sided rings. Okay, now who of you on a very, very warm day, I know we can't even imagine it right now, but on a warm day, you think, okay, the next time I'm going to have athletics or rugby or whatever, I'm going to fill a bottle full of water, put it in the fridge, and then I'm going to take it the next morning. Yes? And then what happens when you open the fridge the next morning? It's solid and it popped, or it broke, or it went open, or whatever. Why does that happen? Because if you look at the liquid phase, the particles can be quite close together. But as soon as it goes into the solid phase, then there's these big spaces between them that causes them to take up more space. Okay, and that is why at the top, the 6-sided gaps with ice at 0 degrees cause it to have a lower density than water. What is density again? Density is the mass per volume, or the number of particles in a certain space. Okay? So when you heat this ice up to form liquid, then the particles are closer together. That is why the density of water increases when you heat them up. And that is why ice floats on water. And that is why Antarctica and the North Pole, whatever, floats on water. And that is why we can live. If water was not angular, and if that did not happen, then we would not live or exist today. Did you know that? That is crazy. Okay? And that is why if we cause the ozone layer to go bigger and bigger, which currently it's not, it's crimping down again, thank goodness. But if it was bigger, and more UV rays come in, and all the ice melts, then all the water level will go up, and, well, we in Paris might become a beach town, an ocean town, live by the beach. Eh? That would be nice. Not? But all the rest will be dead. Okay. All right. So as you can see, I did not highlight so much. It's just the thought that you should know that the density is the most with water, with the liquid phase, and you should know about these gaps between them there. Okay. Right. And then the last type of intermolecular force that we have is ion dipole forces. Okay. Now an ion is, in brackets, we know now it's not exactly that, but it's when a metal is bonded to a non-metal. We actually know it's when the electronegativity is greater than 1.7, I think. Yes? Okay. But it's a metal with a non-metal. Okay. Or it is a salt. Salt. Okay. And a dipole, we know, is something with two poles. Now, ion dipole forces, we find the most when we have a salt that we dissolve in water. Okay, that's the one that we use the most. The water dipole. Okay, so these forces are very, 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 very strong because this ion here, the ion here is a permanent big ion. It's not a positive and a negative side. It's just a positive thing or just a negative thing. Okay, so very negative, very positive. So it's quite strong, this force. Here you can see is the water molecule. We have oxygen here and hydrogen here. Oxygen becomes slightly negative. Hydrogen becomes slightly positive. Okay, so here we have the positive side and here we have chlorine negative, and that attraction force between them there is an ion dipole force. Between an ion and a dipole, we have an ion dipole force. Okay, but you can see there's lots here. I wanted to say something here. Okay, so I'm going to draw an arrow to the bottom. Okay, so this is that is shown there at the top, is when you have a salt crystal, table salt, for example, a salt crystal, and you dissolve it in water. So in the presence of water, you dissolve it. Then you get the sodium ion aqueous, and you get the chlorine ion aqueous. Okay, so what does that aqueous mean? It means solution. It means surrounded by water. So can you see there at the top? You have the sodium ion okay, so at the top there, you see you have the sodium ion surrounded by water. Chlorine ion surrounded by water. So that which we wrote down is represented at the top. Okay. Right. So just a quick summary of the intermolecular forces that we have. We have the London dipole, hydrogen bonding ion dipole. The London forces between temporary dipoles, dipole is between permanent dipoles. Hydrogen bonding is it's a permanent dipole between hydrogen and nitrogen, hydrogen and nitrogen, or hydrogen and fluorine, or hydrogen and oxygen, fluorine. And then ion dipoles is between an ion and a permanent dipole, like water. Okay, so the London forces happens between, and what I want to write down here is, what's wrong? Okay, happens between, here I want to write down, this is when we have symmetrical and non-polar molecules. Symmetrical and non-polar molecules. Is it strong or weak? Very weak. And the melting and boiling points? Very low. Low. So at room temperature, what phase do you think molecules with London forces will be? Gases, because they've already boiled and melted at low temperatures. At room temperature, a gas. Then permanent dipoles gives us dipole forces. That is between asymmetrical and polar molecules. But it's not that polar. Okay, it's not hydrogen something. It's not that polar. So it is just weak. It's not very weak, it's just weakish. And the melting and boiling points are relatively low. Then hydrogen bond is between hydrogen and one of those three. It happens between small, strong electronegative atoms and hydrogens, or hydrogen. And it is very polar. Sorry, very polar. And it has a strong strength, and melting and boiling points are high, medium to high. The one that I want to write down very strong at is iron dipoles. This one is the strongest one. This one is very strong and very high. And that is between salt and water. Okay, let's just see. You see there's your homework on page 60, number 1 and 2. I am going to go on, but just so that you see. They asked, they arrange the following gases in increasing order of being polar. So you must just think about their polarity. And then why is the boiling points of halogens, or why does it increase as you move down the group? Okay, so I'm not going to give that for you. I want you to think a bit. Then we are going to go to the effects of intermolecular forces. Yes. Okay. The effects of intermolecular forces. While she's writing that down, I want to... We're going to look at a few of them. The first one is surface tension. Now, tension is obviously when there's a bit of a pool or a fight going on. So, surface tension refers to the strength of intermolecular forces between the particles of a surface on the surface of the liquid. So, surface tension, if you look at the picture there, refers to that there. At the surface, at the top, at the end. How strong are those intermolecular forces? They're keeping the object together. Okay. Now, before I'm going to go on there, I want to do an experiment. And those of you at the back, you can come forward a bit if you want to. I think you want to come forward. Okay, right, so here I have, you two might want to just turn around. Okay, so here I have water and I have chloroform. Where did people, not anymore, but where did people use chloroform? Yes, for anesthesia. Okay, and here I have water. Right, now, if I pour water out, can you see that it sticks together, it forms a little bubble. Then you all know that you see this everywhere. Okay, now if I come back in 5 minutes, will it still be there?
Yes.
In 5 minutes, yes, it will still be there. Okay, here I have chloroform. Okay, and you can see when I do this with water, it wants to pull back together. Okay, alright. Chloroform. I just want to have a good nap. Can you see chloroform does not do that? It doesn't make a bubble. Okay, it spreads out. Okay, it spreads out a lot. And if you do this, it doesn't keep together like water now you'll see I will use it a lot now, but let's look at this bubble. Can you see it's already drying? It's already going out. There's no surface tension and it's already evaporating. Now, I'm going to speak there and then, but I want you to stay there because after a while this will have evaporated completely. And I want you to put your hand there. Okay, I think today you won't even feel it. But it is actually an endothermic reaction. It cools down everything here. Okay, don't worry about it, it's also a heating agent.
Is it because of the density?
It's because of the weak intermolecular forces. You can see it's evaporating. Can you feel my hand? Completely different, very cold. Okay, so you can see it's already evaporating a lot and very fast. And the water, is it evaporating?
No.
No. Can I leave this bottle open, do you think?
No.
No, it will evaporate and we will all not die, we'll just be on another level.
We'll be high.
Okay, so you can see this, I think maybe by the end of the day, maybe tomorrow it will have evaporated. It's actually tomorrow. But this, on the other hand, it's not even 5 minutes. It's not even 2 minutes. Alright. Okay, you can go sit down. It's evaporated faster than I thought it would. Alright, so because water has strong hydrogen bonding between the water molecules, it gives it a high surface tension. Strong, a high surface tension, causing the water droplets to maintain their characteristic curved form. So it causes it to stay that curvy curve. Whereas liquids with weak intermolecular forces, like we just had, we had chloroform. I just want to check this one specifically. Is CHCl3. Chloroform. Let's just stick with chloroform. Has very little to no surface tension. Okay, we saw that it just went out and it evaporated completely. Okay, then vapor pressure. We spoke about vapor pressure in grade 10 very quickly. Vapor pressure is the pressure that the vapor molecules exert against the size of a container. Definition there. No, that's not the definition. The block is the definition, sorry. Okay, vapor pressure is the pressure that vapor molecules exert against the side of a container. So, how much these gas particles collide. Then, all liquids evaporate spontaneously. What does spontaneously mean? That is simultaneously. You had me there for a moment. I was like, no, that's not it. Without extra help. Okay? So some people will spontaneously answer questions and other people must be asked to answer a question. Okay? Alright, so without extra help, spontaneously by itself, liquids evaporate spontaneously at all temperatures. So you saw that with this chloroform, it just evaporated. This water, Monday morning when you get back, will it still be here? No. Do you think this weekend I put a flame down here so that it evaporated? No. Right? It will, by the energy and the heat in the environment, not that there's a lot, but it will take that energy and it will evaporate by itself. So the substance doesn't need to boil to evaporate. It can just evaporate. No, it depends how cold it will become this weekend. Maybe Monday morning is still there because we all froze to death.
So if it's cold, it freezes. So if it's a good warm, then it evaporates.
Yes. But I don't think it will freeze. Not about ice yet. Okay. Then the definition there of vapor pressure is the pressure exerted by vapor at equilibrium. At equilibrium, I'll speak about that in a moment. With its liquid in a closed system. Okay, so just when we have a container and the lid is closed, okay, and that liquid is allowed to evaporate. then we can fully determine what is the vapor pressure. Because if it's open, the particles will go away and we won't know what is the vapor pressure. Okay, but when it's closed, we can have a better idea.
That's how we see it right now.
Okay. Now, what's wrong? Bukumusuk, ask, what is it?
She said that we did discuss all this last year.
Yes, we did. Wait. Okay, so if you look there at the top, you see there, this container is now open, so this is not a closed system like this. So here we have a closed system. Okay, and when we have a closed system, that can give us equilibrium. Equilibrium. Okay, now equilibrium in this instance, example, is when we heat this up, when we make this warm, the gas particles will evaporate, but it can't go out because it's closed, so it will evaporate until a certain point when it's full, it can't evaporate anymore. Then the particles will be so close together that it will form intermolecular forces again and it will condense. But then there's a gap. So then another particle evaporates and then it pushes them together again and then it condenses and evaporates and condenses and evaporates, and that is called equilibrium. As the one thing happens, the other one happens at the same time. Okay, right, yes, well. Okay, so if you look there at the top, now we have an open system, so it can evaporate. All right, now if we compare, and I know we did this last year, but I want to compare two substances now. I want to compare, let's say we have water in here. So we have H2O, and in this one, the same amount, same temperature, same everything. We have chloroform that we just have. Okay, and we heat them both up on a table to, let's say, 50 degrees Celsius. Okay. Do you think there would have been a lot of chloroform that would have evaporated at 50 degrees Celsius? Yes, almost all of it actually. Okay, so we will have a lot of vapor particles busy going into the atmosphere. At 50 degrees Celsius, water, do you think a lot of it will have evaporated? No, a bit, maybe some, maybe 10 particles. Okay, but not a lot. So why will this have a lot of particles and why will this not have a lot of vapor particles? Yes, this one has weak intermolecular forces. Oh, sorry, don't write skew like me. Sorry, Ella. Okay, I want to make 4 things. 1, 2, 3, 4 things I want to say. What type of intermolecular forces does it have? When it's very weak? London forces. So when I ask a question like that, you first state the obvious. What does it have? It has London forces. Then you say if it's weak or strong. London forces are weak intermolecular forces. Thus, will it need a high temperature to evaporate? No. But now we have a fancy sentence saying what I just said. We say, thus, less energy needed to, can we say to break the forces? No. To overcome the intermolecular forces. I feel like you guys learn more when I'm not here. Okay, there's less energy needed to overcome intermolecular forces. What are we looking at? We're looking at vapor pressure. So we're going to say, thus it evaporates faster and has a higher vapor pressure. Okay, we're going to write this a lot, so get used to it. But I can write the opposite for water. I can say water has hydrogen bonding. It has strong intermolecular forces. So it will take a lot or more or very much energy to overcome intermolecular forces. Thus it evaporates slower and has a lower vapor pressure. Okay, right. What's wrong? You just don't take enough oxygen. So why do you yawn? You yawn because you need oxygen actually.
No, but like after that you get dizzy. Or when like stand up quickly and then it's like,
Yeah, I think it's just because you didn't take enough oxygen, or the oxygen. Why you stand up quickly, I don't know. But I know you yawn. Why do you yawn when you are tired? When you're tired, your body breathes slower and slower, so you don't take in enough oxygen, and then you yawn to get more oxygen. Why do you hiccup?
no, I think it's the transport.
Yeah. Why do you hiccup? Because you take in too much oxygen.
Why is it contagious?
That I don't know. But did you know, but so you probably know this, in life sciences, your earlobe, you either have a straight earlobe, like it goes, I'm looking for someone that has one, I think Karabo has one. So her earlobe doesn't make a lobe like mine, okay? Or like Tazwar, or like Watermelon. You see there's a lobe or straight. That is genetically. So it's also, so it's something obviously you can't change. Also, if you can roll or make your tongue in a loop like this.
Oh, yes.
Not everyone can do it. Can you do it?
Oh, no.
Back to Sanji's Tim Picasso, thank you.
So I was saying, there are 4 points.
Yeah.
Yeah, there is already actually going to be used.
We're going to use it in what?
It's not popping out exactly.
Yes. Yes. This is the chapter that we didn't complete. Yeah. We can do that question when we're done. Yes. Okay. Right. Here quickly we speak about open and closed systems again. So this is our open system. Here is our closed system. Okay. Then it says that if a liquid is allowed to evaporate in a closed system, an equilibrium is established between the liquid and the vapor. This happens as soon as the vapor is saturated at a specific temperature. What does the word saturated mean? Full. You know, people sometimes say they're full.
Then what do they mean if they say it is allowed?
If nothing prevents it from evaporating. So it's just when there's enough space. Okay, so this is what I just explained. I said if it's open, then it can just evaporate until you have nothing left. Whereas if it's a closed system, it will evaporate until it's full, saturated. And then it will condense again and evaporate and condense and evaporate. And that is called equilibrium, or a dynamic equilibrium. Okay, so this happens when the quantity of liquid and vapor pressure stays constant. And when the rate of evaporation, what does rate mean again? Divide by time. So how fast the rate, how fast it evaporates is equal to how fast it condenses. Yes. I can't hear. Can I? Cool drink, yes. But it depends what you mix it with. If it's very sugary, then the intermolecular forces are strong. And it struggles to evaporate. Most definitely it can evaporate. Alright, so This question we just answered at the on the previous page, but now they ask it just a bit differently. Here we only looked at chloroform when I answered the question. Okay, but now they ask you, you must compare. Why is the vapor pressure of chloroform higher than that of water? So it's not just chloroform, they want you to compare. So you must mention both. So this chapter in grade 11 is a chapter where you're going to write a lot. Science, we don't normally write a lot, but this one, get ready. It's business studies. We are writing. Okay, so when you do questions like this, you're always going to write 4 bullet points. Always, always, always. The first bullet point, you always say what type of intermolecular force is present. What do we have? What are we busy with? Okay. Or in brackets, or I want you to say what is the obvious Thank you. Obvious difference between the two. This one is long, this one is short. This one is polar, this one is non-polar. This one is the obvious difference. Then you're going to say about the strength of the intermolecular force. Is it strong or is it weak? Then you're going to speak about the golden sentence that speaks about the energy. And then you are going to make your conclusion. Sorry, I started with 1 and then I went on to bullet points. It's 1, 2, 3, 4. Okay, so what is the obvious difference between chloroform and water in terms of intermolecular force? London and water is hydrogen bond. So you are going to state it. You're going to say chloroform has London intermolecular forces and water has, and now I'm going to abbreviate, but please don't do that in a test, hydrogen bonding. Okay, we're going to stop there for today. You know what your homework is? Number 1 and number 2. You must enjoy your weekend, stay warm, don't freeze. It is too cold. Alright, to my auntie, tot ziens julle. This one. Hoekom?
That's what she's in pain. That's what I'm saying.
So what was I derived from your comment?
Maybe we start giving sweeties out.
Please, man. Well, you can't say please. You must.
Please, ma'am.
Please, man.
I said, please, ma'am.
Because she won't be waiting for me on Friday for my extra classes. So, and she cannot go out.
Where do you live? This right. You don't have to put that in, give it to Dion. You know who Dion is.
I'll tell her she knows that.
Okay. I guess I think we say add here it's a class now. So ik zie maar dat het vaak kan. Voor het jaar verschillende mag. Ja, dan zij wil in baie vanaand sien kan. Nee, soos ek dit voorkyk.
Ja.
So dit is 'n verandering. Wat ek nou vir jou wou sê, notas. Maar goed dat ek wat ek weet jou